Welcome back, hyperbolic coding chamber extraordinaires. It's day 57 of daily LeetCode, daily LeetCode, day 57. So we are back once again. We are still getting absolutely bodied by evaluate division. This problem was written by Aristophanes himself, the great Greek mathematician. As well as a collaboration by Picasso and Albert Einstein. They all wrote this problem together and they've passed it down, passing the torch, much like All Might passed the torch to a young Midoriya. This problem has been passed down from every mathematician since time immemorial. So this is actually people actually don't know that this problem is actually unsolvable. If you click solution, there's actually no solution. This is actually true. So it's accepted, right? This is really really just a hot fix by the LeetCode team, right? If you do an inspection on this page, what you're gonna see, right, is that it's literally a div, right, and it's blocking the number 0. There's actually a little script that says finds this element with the selector and changes the value to 297. Pull up the network request though, the actual accepted number pulled back from the API on LeetCode is 0. So this problem is actually unsolvable. That being said, we have acquired a set of resources to solve this problem. So if we do solve it, one could say the HCC is actually paving new ways for the algorithmic community. So we're back once again with 399 reflections. Our boy Thomas mentioned a steezy move for LC 1763 to solve it. However, this is relatively, I'm reading the solution, however, it just doesn't quite make sense to me. Yeah, I really have a trouble, I tend to be I have to like work it out myself. So I'm reading this, right? But I guess the method is so far from my method that I'm struggling to understand. So I think we're gonna hit my boy Thomas up. We're gonna get the code from him, right? And then from there, I think maybe we can figure it out. But don't want to spend too much time, right? Because we have to be working on the highest priority problems to be making the most progress that one can make. That being said, right, let's see what problems we have due. Right, we have no problems due. So, we're just going to do some more reviews. So probably, as usual, 30 minutes of review, right? And then we're going to throw in the hour into the thing, right? Into evaluate division. However, right, I've also noticed that we're incapable currently of solving mathematical equations, right? So I have a bit of a Wolfram Alpha cheat code pulled up, right? Because I actually forgot how to do 4/A, how to solve this, right? But we are able to remember, right? We were able to remember. What else was I gonna say? Oh yeah, also, right, I have a plan of attack to solve this evaluate division problem by under the great tutelage of the Copy Ninja. We have acquired very legally. We have very legally acquired a copy of the algorithm design manual. This was procured through a very, very ethical distribution source. So we are currently reading the algorithm design manual. Definitely some gems in there, right? But I think we're just gonna have to use it as a reference book. I read chapter 1, I think so far in chapter 2, some actual fire gems. So if you're looking for a way to supplement your algorithmic grind, this is the cheat code, and it has been paved by the Copy Ninja himself. So you're actually losing out by not buying this book or acquiring it through an ethically sourced distribution channel. Additionally, right, I'm pretty much starting to search into the book looking for like something about disjoint sets or union finds. We found some content, right? But unfortunately, I was reading for like an hour and a half today, right? We read for like 30 minutes yesterday, right? But it goes slower. And I'm trying the exercises. So I'm trying the exercises, so it goes slower. I learned a lot about the knapsack problem, trying to figure out a basic example and also about mathematical terms. That being said, a lot of cheat codes in there. I'm hoping that by reading stuff on union find and disjoint set in the evaluate division, that we can make better progress through. But I'm also reading about. I'm also thinking like there's not really a lot in there specifically about like union find. I'm reading an example right now. Maybe we'll figure out what we need. But additionally, I think I just need a better grasp on graphs in general. So that would probably be the goal to start there. And then, yeah, so I might just read the union find or disjoint set chapter, and then go into, well, it's actually complicated, right? Because the disjoints, the disjoint set or union find is actually included under the set data structures, I think, chapter. And yeah, so it's a bit all over the place. So I'm thinking after we read that chapter, right, tomorrow we should be even better. So I was reading a lot today trying to get a new way to tackle this problem. Unfortunately, we didn't get to do that. So we're still a bit stuck here. But we have to try every tool in our arsenal. Even though there's no tools remaining already, we just need more tools for graph problems. That being said, I need to read more about graphs in general. So I'm hoping after tonight and after tomorrow, I have a bit more information to tackle this problem from a different angle. So I'm wondering from what angle should we really try and review today? Maybe we'll do an hour. Actually, I'm thinking maybe we'll do I don't know how much value there is in me trying again from this angle, because I'd like to get more information about a new or novel method to attack it. Made some progress yesterday. Still going to spend some time today, so we'll do 30 minutes, but I'm thinking we're going to do an hour of just regular review, reviewing old problems. Maybe we'll set new bars for problems, right? So we'll try and take each review problem to its max. Then when we know the solution, we'll just regurgitate it because we've already memorized the mental structure. But I guess the goal, right, as always, is we have a noob solution, brute force solution that I write, right? Explain it every time I come into it. Try explaining it a different way. Explore paths of explaining it, right, as a vehicle to learn, and then from there, hopefully over time we acquire new information so we can iterate on it, right? So I think it's a very natural way to grow our skill level. Additionally, learn to define or model problems in ways that I guess fit into our current sense of like how we model problems. So I'll read a solution sometimes and I'll be like, I know this solves a problem because it's in the solution tab. However, how I would solve this problem, like with my own intuition, is just completely not included here. So it sometimes seems like the solution is just not compatible with the current structure in my head. So that being said, I think this version allows me to kind of build my own structures and use my own tools, which I think is good because it's interesting when I figure out a solution myself using my own way, right? It's very natural because it's kind of novel in a sense to me. And so I end up like remembering it very intuitively. Like once I do it once, I'll just remember it forever. But when I read someone else's solution, I'm just like, oh, I don't know if I still remember how to do this. It feels more like I'm doing a performance, like regurgitating. That being said, I don't know if there's much value to doing evaluate division since we don't really have a new novel method of attacking it, but it's still important to make sure we visit all vertices in the graph, right, of our knowledge structures to make sure that there's no pre-existing way to solve this. And then, so we'll do like an hour of review, right, and then 30 minutes of evaluate division. Also we've added the Tim Cook Pad 3, right? It's really not the 3, it's just an iPad mini. So we're just going to use it because I was writing yesterday, right? I was writing some equations to work on, right? And drawing some graphs for yesterday, but it wasn't really showing up on screen. So it could be a useful tool so that I'm not just talking into the abyss, right? So that is what we will do. And maybe I'm also thinking maybe we'll start including the problems done, right, in the problems done in the video description. So I think that could be helpful. Just maybe as like some sort of indexing. So that is what we will do, right? So we have some review to do, right? And as always, right, last night we had a very, very huge meeting in the HCC about future plans, right? We had a stake and shareholder, all hands on deck, the hyperbolic coding chamber, which is the Discord, right? We had an all hands on deck, and it was a crazy meeting. Big changes coming to the HCC. You're going to want to get in right before it closes. So make sure to join the Discord, and I'm just going to jump into it. So hour and a half as usual, right? And then we're going to do, right, hour and a half as usual. We're going to do an hour of review and then evaluate division, right? And ideally, maybe we'll try to take each problem to a level that we haven't taken it to before. So follow it through so that you know you are fixing the real problem instead of assuming you're fixing it. I actually remember this. Right, so previous mistake we made last time we did this problem, we solved a version of it, right? We ran into some edge cases where it wasn't working, mostly because of misunderstanding with how JavaScript handles sorts. And then instead of modifying our approach, or instead of making this problem make sense as to why it wasn't working, I just kept solving a problem that I wasn't really certain was a problem or not. So we're just going to do it. Given an integer array nums, return all the triplets num sub I, num sub j, num sub k, such that I does not equal j, the index, right? I does not equal k, right? And j does not equal k. Notice that the solution must not contain duplicate triplets. So I cannot equal j, I cannot equal k, and j does not equal k. Interesting. Num sub I plus num sub j plus num sub k equals 0. I does not equal j. Right, I'm not really understanding how I cannot equal j. How defining it like this, I does not equal j, I does not equal k, and j does not equal k, allows us to not. Actually, I'm thinking an easier way to do it. I think I already have my screen recorded, so I think we can just switch between these two. So I think I can just go like this, and we should be good. So I guess my issue is I'm not understanding why they're saying that I cannot equal j, I does not equal k, and j does not equal k. So let me look at that one more time. I does not equal k, right? I does not equal k, j does not equal k, and I does not equal j. So yeah, they're saying, notice that this makes them incapable of creating, or incapable of, they're basically saying that notice that the set must be unique, right? Notice that the solution set must not contain duplicate triplets. But I'm not understanding how that makes sense. They're saying I cannot equal k, I cannot equal j, and j cannot equal k. So if we had I equals 1, I equals 0, right? K equals 1, and j equals 2, we're saying that 0 cannot equal 1, right? And we're saying that 0, right, I cannot equal j, right? We're saying that 0 cannot equal 2, right? And then we're saying that j cannot equal k, so 1 cannot equal 2. now, right, that doesn't make sense because k is equal to 1. Wait, it doesn't make, I'm confused. J is equal to 2. I think I went in the wrong. Wait, what is going on? How do you move things? All right, this doesn't matter. We said that I equals, we should have wrote it just better, right? Let's just write it like this. And we'll say that I, and the final one was that if we check the original, we're saying that J does not equal K, right? J does not equal K. So if we erase all this nonsense up here, right, I cannot equal K, right? So 0 cannot equal 1, right? I does not equal J, right? 0 cannot equal J, which is 2, right? And then J does not equal K. Well, J is equal to 2. J cannot equal 1. So I guess I don't understand how making sure, I guess I would assume that the case is I cannot equal K, right? I guess I would assume there would be 6 conditions, right? I cannot equal K, I cannot equal J, right? And then we'll have for J, J cannot equal K, J cannot equal K. Then for K, we'll have K cannot equal I, and I cannot equal, I'm still blocking, and I'm trolling. Right, so I think that just doesn't make sense. Maybe there's some compression here. Maybe it's all the same as long as I doesn't equal K and J, right? But I guess I'm not seeing how we're saying I can't equal J. I think I see what's happening. There is a duplication of cases, I think, right? Because I guess what I'm thinking is you'd have 6 cases, right? Because you'd have 3 factorial, right? Which would be 3 times 2 times 1, which would give us 6. And the 6 cases you would have would be I does not equal K, right? I does not equal J. And then you'd have J does not equal I, and J does not equal K, right? And then you have K does not equal I, and K does not equal J. But they've simplified it down to just I does not equal, they've simplified it down to pretty much these 3. Right? Because if we're saying J does not equal I, okay, so we're saying J does not equal I, then we're duplicating it, right? We're saying K does not equal I. All right, so we're duplicating it, and then K does not equal J. Okay, so now I get it. Right? I was thinking there'd be 6 cases, right? But these are just duplicates, so you can cross them all out. So that makes sense. That makes sense. So we can get back to the problem. So if we're given an integer array nums, return all triplets, right? So that none of the indexes are the same, right? And that they all sum to 0. Notice that the solution set must not contain duplicate triplets. Right? So given an array numbers, you have -1, 0, 1, 2, -1, -4, right? And our output is pretty much all the unique triplets that sum to 0. All the unique triplets that sum to 0. Right, and in the explanation, they actually include three triplets that sum to 0, but one of them is a duplicate, right? Because of the set. So basically what we want is a unique set of elements such that they sum to 0. But the group, or I guess the set elements included in the set, I guess the total, I guess we're looking for a set of elements or a set of groups where none of them are unique, or all of them are unique and sum to 0. String triplets are -1, 0, 1, -1. Interesting, right? And we see that for example 2, we have 0, 1, 1, and the only possible triplet does not sum up to 0. And we have 0, 0, 0, 0, 0, 0, 0, 1. The only possible triplet sums up to 0. So there's a few ways you can actually phrase this, right? Knowing that we're looking for sum equaling 0, right? What we can do is we can actually sort our input, right? And if we sort our input, what does that provide us? So we have this input. If we sort it right, we'd have -4. So we'll remove -4 here. I'll make this a little bigger. Right? We have two -1s, right? We remove that -1 here. Right? And the remaining elements are already 0, 1, 2. Right? And what that allows us to do, right, is if we know that if we ever get to an index, right, for example 0, right, we know that everything after 0 is a waste of time. Since our input is sorted, we can't find any other triplets such that it would actually equal such that it would actually equal 0, right? Because once we get to 0, if we consider the next two elements, right, we have 1 and 2, right? All our sum can only be greater than 0, greater than or equal to 0, right? So it's just not going to work, right? So what we can do is sort, and if we sort, we're going to be bounded by at least n log n to start. We can cut, depending on our input, or the sample size, cut our input in half, right? But in worst case, we still have linear operations to do, right? So I think so our input kind of becomes like this. So one way I think we can actually, so our input becomes like this. We have n log n, right? But I think it's also important to conceive maybe what our best conceivable runtime could be. Since we're sorting, we're going to have n log n runtime so far, right? And we know that we have, right, based on other problems, an implementation for 2sum, right, such that we can do it in linear time and linear space, or linear time as long as our input array is sorted with constant space. So there's another thing to consider here basically, right? And I guess I'm kind of jumping around, but another thing to consider, right, is that the sorting method only works because we have to return the numbers that sum up to 0. If we had to return the indexes, right, for example, the indexes of numbers that sum to 0, if we had to return the indexes of the numbers that sum to 0, sorting it would actually destroy our output, right? Because an element at index 0, right, is not -4. All right, so this only works because we can actually return the sum of the numbers, right, and not the indexes themselves. Additionally, we know that we can do 2sum in linear time, right, with constant or linear space, right? And the reason we're talking about 2sum is that we can rephrase the problem, right? So let's just say we change our input a little bit, right? Our input is sorted, right? For a given number, right, -1, right, 2sum, right, takes a subsection of an array, right, and searches that array in some method to find if there are two numbers which sum up to a target value, right? The reason we can augment 2sum to work in this algorithm is that searching up for a number that adds up to searching for 3 numbers that add up to a particular number is simpler because the number that we're looking to add up to is 0, right? So we know that our target is equal to our current number, right? 0 minus our current number, right? And we can see that, right? If we start at index -1 here, and we want to know, right, what our target number is, right? What the number or the sum that we're looking for, the sum of two numbers that we're looking for to equal 0, right? We know that our target is 0, right? So, what's our target, right? It's going to be 0 minus -1. Well, we can change both of these to a plus, right? We get 0 plus 1, and our target is actually going to be 1. So when we're searching on the second half of the array, what we can see is that we're searching for a number for which we're searching for two numbers whose target sum, right, is 1, and we know that we have those two numbers. It's 0 and 1. It's 0 and 1. And I'm also realizing we want to keep those elements in the array. We can't just act like they don't exist, but our algorithm will stop, right, at 0 as its final number, right? Because when it gets to 1, it's going to be greater than 0, which means no further numbers could sum to 0, right? We could have 4,000, because our array is sorted, right? So from here, what do we want to do? All right, so we know that we have a two-sum algorithm, right? N log n, right, with linear time. So it looks like we'll probably be bounded by, we sort, right? We're going to iterate through the array, right? For each element, we're going to run this two-sum algorithm. So you can say that we'll probably be doing n squared, and n squared is worse than n log n. So it looks like our VCR might just be O of n squared, right? So let's see if we can implement that. So what's the intuition, right? We sort the numbers, sort nums, right? And then from there, we'll take a current number, right? And then we'll run with two-sum, right? So we'll sort it, right? We'll start at -4, right? And then we're going to run two-sum on this subsection here, see if there's any number which sums up to +4. There is none. So we're going to go to -1, right? And try to sum up all the numbers which sum up to 1, right? And we know we have 1. It's going to be 0 and 1, right? We have a problem, though, because this would actually give us duplicates, right? We have -1, right? 0, 1. We have another -1 and 0, 1. So I think what we see, right, is that to prevent duplicates, we're actually going to want to make sure that the index we're working on is different than the previous index, right? Because -1, we take I, 0, 1, 2, 2 minus 1 gives us index 1. These two index, the current index and the index before it, are the same, which means the output is going to produce duplicates. So if that's the case, we can keep going until that's not the case. We get to 0, right, our final version, right, and 0 is at 0, right? Is it possible to find a number, right, that's going to sum to be greater than 0? Unlikely, right? But it's possible if there are still zeros remaining. This would be our last one that we try, right? Because it's possible we could have something like this, 0, 0, 0, right? In which we'd have one possible 0, and we'd also skip all these zeros because they would be the same as their previous element, right? So we want to do something about duplicates as well. So now we can implement this, right? We'll do nums dot sort. We'll take an A and B. We'll sort it in ascending order, right? From there, we're going to want an array of triplets, right? And then we'll make this smaller again, just because it makes more sense. Then we're going to take the current number, right? For let I, right? I is equal to 0. I is less than nums dot length. I plus plus, right? We're going to have a particular number. And we're going to want to do that thing we said earlier, right? Which is just make sure, right, that the current value and the value before are not the same. To start, right, we can do nums sub I does not equal nums sub I minus 1. We get a little bit of leeway here, since if we subscript outside of an array in JavaScript, we actually get undefined, which means that for our starting element of -4, undefined would not be equal to -4, so we get a little bit lucky. Right, from there, right, we want to say triplets dot push, right, the toSum of nums, right, and nums, and I think all we'll need is I, which is our current index. At the end, we're going to want to return triplets. We did something about duplicate runs. We're going to run with the toSum. All right, so we're going to need another function, toSum, which takes nums, which would be an array of numbers, right? And it's going to return an array of numbers, right? And we'll say output is going to be an array. If output's going to be an array, right, then we're going to want to make certain that we're just going to say t, or yeah, t is going to be equal to toSum, right? And this is the case, right? If t dot length does not equal 0, then we'd like to do triplets dot push t. This is something I'm noticing. Right, we're going to have an output array, so we're just going to return output. So here we want to do our linear time, right, and linear time and constant space toSum implementation, where the intuition behind it, right, is that we have 2 pointers, right, L and R, working between the left end and the right end, right? And if they sum to the value we're looking for, right, then we're going to add it to our output. Otherwise, we're going to keep going, right? But it depends. If our value is greater than the target, right, then the best way to get closer is to shift to, right, our right pointer down, since our array is sorted, right? And if we're less than it, the best way to get closer is to actually increment our left pointer, right, to give us the next smallest value we can add without potentially going over it. So that's the case. To start this, right, we're going to need a target number. Like we said, our target number is going to be equal to 0 minus nums, right? And we're going to pass in I, which is going to be our start index. Or we'll just call it, what should we call it? We'll call it our seed index. Makes potential sense since we're seeding it, nums array, with this value, right? We're using it to calculate our target, right? Then we're going to have our left, right, boundary, which is actually going to start at seed index plus 1, right? Because if we want to find the triplets that sum up to 0 starting at -4, we don't want to include -4, right? Because then it would be impossible, right? It also wouldn't be, actually it wouldn't be impossible, but it would include duplicates, right? Since if I is going to be 0, then j can't be 0, k can't be 0. So you want to shuffle that out, and we'll say right is equal to nums.length minus 1, and then we'll say, well, left is less than right, right? Then we're going to do our work here. We're going to say if, right? And typically it's kind of like a binary search a little bit. We're going to want to figure out our sum, and our sum is going to be equal to, right, our nums sub seed index, right? And actually there's a couple ways to do this. We can just add the numbers all together, or we can say target, right, plus nums sub left plus nums sub right, right? And if that sum equals 0, we're in business. So I guess we could remove target and just say num sub seed index. We'll say if sum equals 0, right, then that's awesome. We actually found a new sum, right? Not a new sum, but a new group of numbers which sums to 0. So we can do output.push, and we want to push this group of tuples, this group of values, right, be nums sub seed index, right, nums sub left, right, and nums sub right. All right, but additionally, we're also going to want to do one more thing, right? Because if with this current version of the algorithm, right, we're gonna have an else if, right? And then we're gonna have another else if, right? The problem being that both of these other else ifs are going to make a progress step for left or right, either moving left up or right up. When we find a sum that equals 0, we're actually not doing anything, right? So we're gonna want to do left plus equal 1 to move it forward, right? And it's okay to move it safely forward because it means we've already found a triplet using left. So it's okay to move it forward. It can't be reused because it would give us another duplicate, but right can be reused. So we don't move right down, right? And so I'm just gonna make this a bit wider. We'll say if sum is greater than 0, because 0 is our target. Sum is greater than 0, then the best we can do is actually just decrement right? And the reason is because our sum is greater than 0 currently, which means to get it below 0, best we can do is actually decrement, go down one, right, go down or go left one index, right? If we're at 2, right, best we can do is go down to 1, right, and maybe something on the left hand side can fill that hole. And then we're going to do something similar here. We're going to say if sum is less than 0, well, we can't go left because if we go left, we'll actually be even smaller. So we want to go up, right? And I think we're going to want one more step like we did earlier, right? Because this is also possible in our two-sum implementation, right, to run into duplicates. So there's two cases here. Our if statement here prevents us from using a seed index that is a duplicate index that we've seen before. But also we want to prevent using left and right boundaries that are also that can also create duplicates for us as well. So one way to look at this right is if we're at -1, right, our seed algorithm is going to give us negatives 0 and 1 as a potential answer, right? But it can give us -1, -1, and 2 as an answer, as well as -1, -1, and 1 as an answer. But similarly to how when our seed number, we only want to do work when our seed number and the previous number aren't the same, right, to prevent duplicates, we're going to want the similar action for our two-sum loop, right? But where does it go, I guess, is the question that I guess needs to make the most sense. Left is iterating all the way up to right basically until it's done. So we're going to want to make sure that num sub left and num sub left minus 1 are not the same. So we could do, and maybe this is a little strange, we could say if num sub left equals num sub left minus 1, then respectfully we'd like to skip this iteration, but we don't want this loop to run ever. If we wrote continue here, this loop would run forever whenever there's a duplicate value. So we'll say continue, but we're also going to want to do left plus equal 1. So let's give this a shot. So we're getting non as an output, right? Because we're pushing t, right? It looks like the what we're pushing on as output here might not be making sense, which we're pushing on an array, 3 values of num sub seed index, num sub left, and num sub right. We return as output, we do output.push. I guess my question is, why is it not a number? So there must be something off here. Num sub left. This is an array. I guess let's follow it through. We sort the array, right? We get what we thought we would, right? Because we're sorting it as usual. We say I is equal to 0. This is nums.length. -4 is not the same as undefined, so we're going to do t, or the toSum dot length, right? toSum of nums and I, right? So output is equal to an array I'm also saying we're going to want to spread that array. If we're returning an array, we're basically going to be returning an array of an array of numbers, right? Because we're pushing on to an array here. We're going to want to spread that value into tuples. I think that could have been the issue. Okay, so we're getting more numbers now, which makes sense. So let's see what's happening here. We're only getting -1, 0, and 1. So we know that for -4, right, there's no number that can give us what we're looking for. But for -1, we know that we're getting -1, 0, and 1. We also want -1, -1, and 2, right? But we should be able to get that to start. When we use -1 as our seed number, right, the first one we look at should be -1 and 2. So it's actually kind of strange that we're not getting the number we thought we would get. So if I get my seed index is so our seed index is -1, right? Our left pointer would be -1 here, right? And 2, and then we're going to say if num sub left is equal to nums sub left -1, which it is. So we're actually, so we're actually going to skip it, and then we end up calculating -1, 0, and 1. So that actually makes sense. I think what we're seeing though is that I think I see what's happening here. It seems like we want to skip creating duplicates after we've already found a safe version, right? So I'm certain if we run this, we'll get more value, like all the values we need, right? But we still have a potential for duplicates. for not generating all of we should still need a way to more accurately remove duplicates. Right, so I think that's what we're seeing here with all the zeros here. I should have been able to generate a counterexample for that now that I'm thinking about it. Because clicking submit kind of didn't actually have to force me to think about it. Right, so we know we have 0, 0, 0, 0, 0, 0. Right, and what's happening there is on first iteration, right, on first, when we sort this, right, we have 4 zeros. We use our first 0 as a seed index, and then we search, right, for a sum that will get us to 0. Right, well, this number and this number will get us to 0. Right, and then when it does, we increment left plus equals 1, which means that we can now use these two zeros to these two zeros here, plus our first 0 to give us a sum of 0, which gives us a duplicate 0. Right, so I think what we want is after we push on something onto the output, we're going to want to go forth and skip those values. Right, so if we know that this first 0, the second, gosh, the selecting here is just strange. The first two zeros and the last 0 give us a sum of 0. Right, then what we're going to want to do is make certain that we keep iterating forward until these two zeros aren't the same. So we'll do while left, right? While left, we'll say like we did earlier actually, while nums sub left is equal to nums sub left minus 1, do left plus equals 1. Right, so we do left plus equals 1 once. Then we check behind us. Is it still 0? Yes. Then we go to this 0. Is it still 0? Yes. So I think if we change, let's run it for our original case to see if it still works. So it's like we're never running. This is strange. Oh, I think I see what's happening. We have to increment it once, at least first, and we have to make sure we're actually solving the correct problem. So let's say we had before, right? We know that these first two zeros plus the last one give us a sum of 0. From there, if that's the case, right, then what we're going to do is increment while num sub left, which is this index, is equal to num sub left minus 1. So we do left plus 1. Are they the same? Yes. Are they the same? Yes. Now num sub left is equal to undefined, which doesn't equal 0. So we actually should be ending here. It's unclear why we're not actually. Maybe what we're doing is actually incorrect though, because what we're doing is checking that we're different from the value before us, but we want to make sure that there's no duplicates, which is by checking the value in front of us. Could that make a big difference though? We do plus left, right, num sub left plus equals 1. We check in front of us. Are they the same? Yes. We increment. Are they the same? Yes. All right, then we check, are they the same? 0 undefined, they wouldn't be. Yeah, I'm not understanding why that runs forever. Oh, I see what's happening. Yeah, you need some sort of progress step. You need a basic progress step. I don't think it matters if you do num sub -1 or +1, but if you imagine it like this, with up here, right, let's say we find a pair that equals 0. We have -1, 0, right, and 1, right? We know it equals 0. We know the sum is equal to 0, right? But if you remove this one right here, well, num sub left does not equal num sub left -1 because -1 is not equal to -4. So then we just keep recalculating this over and over and over again. So you need at least one progress step to kick it off so you don't end up in an infinite loop. This edge case ultimately helps us to catch when values are very similar next to each other. When they're not, it creates an issue. So I think if we run this now, it should work. And I think it should also work if we do -1 as well, though we might have to increment 1 index forward. We added an R by mistake. So I think this works, and I'm guessing the time complexity would be n squared ultimately, even though we're sorting, but n squared ends up dominating. N squared ends up dominating n log n for sort. So I think we end up being okay here. Goal time would be O of n squared. I wonder if a linear time solution could be done. And actually thinking I'm going to stop there actually, since we read for an hour and we're for an hour, almost 2 hours, hour and a half, almost 2 hours of algorithm design, then about 45 minutes of actual algorithm work. So I think we're going to stop there for today, and then we shall return tomorrow.